Hello there, and welcome to the Sleepy Science Channel. I'm absolutely delighted you're here with us tonight. Perhaps the day has been a marathon, a whirlwind of activity that's left you yearning for tranquility. Hello there, and welcome to the Sleepy Science Channel. I'm absolutely delighted you're here with us tonight. Perhaps the day has been a marathon, a whirlwind of activity that's left you yearning for tranquility. Or maybe you're one of those kindred spirits who find solace in the cosmos, preferring to drift off to dreamland contemplating distant planets and their ethereal moons rather than counting the same old sheep jumping over the same old fence. Either way, tonight's voyage is tailor-made for you. There's nothing you need to do now, no effort required, just pure, unadulterated rest. Allow your breath to deepen and slow, let your thoughts soften around the edges, and feel your body becoming listless, as if gravity itself has loosened its relentless grip, and you've begun to float effortlessly through the vast expanse of space. Because tonight, my friends, we're embarking on a gentle, meandering drift through our solar system. Not a rigid, straight-line trajectory, mind you, but a series of soft, languid spirals. We'll journey from sun-drenched planets and shimmering dusty rings to shadowed craters and the enigmatic frozen oceans hidden deep beneath layers of ice. This isn't a story told through dry numbers and cold calculations, but rather through the vibrant language of magnetic storms, the intriguing dance of tilted axes and moons that possess the magical ability to glow in the dark, from worlds that seem to be perpetually sideways and rains composed of glittering diamonds, to the ancient sunlight that is still faithfully traversing the seemingly endless void. Every single orbit holds within it something utterly strange and breathtakingly beautiful. We will proceed slowly, deliberately, gently, revealing just one sleepy fact at a time, allowing each morsel of knowledge to gently lull you towards slumber. And just before we fully begin our cosmic exploration, if you find that these quiet, thoughtful journeys help you to unwind or offer a peaceful and satisfying way to conclude your day, I would be deeply grateful if you would consider gently tapping the like button and subscribing to the channel. It helps others, equally weary travelers, find their way here too, one sleepy soul at a time, seeking refuge in the wonders of the universe. Now, let's truly begin. Neptune's winds surpass the speed of sound. It seems almost paradoxical, but despite its status as the most distant known planet from the Sun, Neptune is home to the fastest winds in our entire solar system. These ferocious winds relentlessly whip through its upper atmosphere at speeds exceeding a staggering 2,000 kilometers per hour. That's faster than the speed of sound here on Earth. To put that into perspective, it's roughly 5 times the speed of a commercial jet airplane soaring through the skies. The source of this immense power is thought to derive from the planet's internal heat, a primordial energy that continues to radiate outwards despite the utterly freezing conditions that prevail at its surface. Neptune's atmosphere is primarily composed of hydrogen, helium, and methane, and it is these winds that carve out massive swirling storm systems into the planet's pale blue clouds, painting an ever-shifting masterpiece across the face of this distant world. It's a frozen realm caught in a state of constant supersonic motion. Mars harbors a canyon the size of an entire continent, stretching for more than 4,000 kilometers across the Martian equator. Valles Marineris is the largest canyon system not just on Mars, but in the entire solar system. Its sheer scale is difficult to grasp. It would span the entire width of the continental United States, from the bustling shores of the Atlantic to the sun-kissed beaches of the Pacific. In certain places, this colossal canyon plunges to depths of over 7 kilometers, making it more than 5 times deeper than the Grand Canyon here on Earth. Scientists believe it formed through a complex interplay of tectonic stretching, intense volcanic activity, and relentless erosion over eons. Unlike Earth's canyons, which are typically carved by the relentless flow of rivers, Valles Marineris may have opened up as the planet's crust cracked and pulled apart. A slow-motion geological cataclysm, it stands as a stark scar upon the face of Mars, hinting at a violent and tumultuous geological past, now frozen in time. Venus possesses no global magnetic field. Despite being remarkably similar to Earth in terms of size, mass, and overall composition, Venus is conspicuously lacking in one crucial planetary feature: a global magnetic field. Earth's magnetic shield is generated by the dynamic motion of molten iron swirling within its outer core, protecting our planet from the constant barrage of harmful solar radiation. Venus, however, appears to possess a sluggish or possibly even solid core, which may be preventing the kind of dynamo effect necessary to generate such a protective field. Without this vital shield, Venus's atmosphere is constantly bombarded by the solar wind, which has gradually stripped away lighter elements over immense spans of time. The absence of a magnetic field helps to explain why Venus, once potentially Earth-like in its early history, ultimately transformed into the scorching furnace-like world we know today. Diamonds might actually rain down on Uranus and Neptune, deep within and on these laboratories. If this one of these Mars and Earths, while we often imagine asteroids as solitary wanderers drifting alone through the emptiness of space, the reality is that some of them actually have moons, smaller celestial bodies orbiting around them. These tiny satellites are usually captured fragments of other asteroids or co-formed companions that arose alongside their larger parent body. The first asteroid moon to be discovered was Dactyl, which orbits the asteroid Ida, revealed in stunning detail by the Galileo spacecraft in 1993. Since then, dozens more asteroid moon systems have been found, including some with multiple moons or strange binary arrangements where two asteroids orbit each other in a delicate cosmic dance. These miniature solar systems demonstrate that even in the vastness of space, gravity can link even the smallest of objects into quiet, drifting partnerships. Mercury has a ghostly exosphere instead of a true atmosphere. Unlike Earth, Mercury doesn't have a thick atmosphere capable of retaining heat or scattering light to create a vibrant sky. Instead, it possesses a thin, tenuous shell of particles known as an exosphere, a near vacuum where atoms bounce around without colliding with each other. This exosphere is composed of atoms blasted from the surface by the relentless solar wind and the constant bombardment of micrometeoroid impacts, including elements like sodium, potassium, and oxygen. Because Mercury lacks the sufficient gravity to hold onto a real atmosphere, these particles constantly escape into space and are replenished from the surface. The result is a ghostly, shimmering envelope of scattered atoms, invisible to the naked eye but detectable with specialized scientific instruments. The Sun loses millions of tons of mass every second. Every single second, the Sun converts over 4 million tons of its own mass into pure energy through the process of nuclear fusion. Deep within its core, hydrogen atoms are fused together to create helium, releasing the light and heat that power our entire solar system. This immense energy radiates outwards in all directions, warming planets, driving winds, and ultimately fueling life here on Earth. Though this mass loss is minuscule compared to the Sun's total mass, over billions of years, it certainly adds up. Eventually, the Sun will exhaust its hydrogen fuel and begin to undergo dramatic changes. But for now, it continues to burn steadily, sacrificing a tiny part of itself with every passing second to sustain our corner of the cosmos. Saturn's rings are slowly disappearing. The breathtaking rings that encircle Saturn are not permanent, timeless structures. In reality, they are gradually falling into the planet, drawn inwards by Saturn's powerful gravity and pulled downwards by its complex magnetic field. This process, often referred to as ring rain, involves streams of ice particles and charged material drift inwards over time. Observations from the Cassini spacecraft suggest that the rings may be less than 100 million years old, which is remarkably young by planetary standards, and could vanish entirely in another few hundred million years. Though they may seem timeless and eternal, Saturn's rings are in fact a temporary feature, a shimmering spectacle that will one day fade into memory. Mars experiences planet-wide dust storms. Mars is renowned for its rusty, desert-like landscape, but it's also known for the colossal dust storms that sometimes engulf the entire planet in a swirling haze. These storms can last for weeks or even months, blocking out sunlight and dramatically reshaping the Martian surface. The dust is incredibly fine and can remain suspended in the atmosphere for extended periods, creating a hazy, reddish glow that obscures the entire planet. Some storms begin as small, localized gusts, but can rapidly grow due to feedback loops between heat, wind, and the planet's unique topography. In 2018, such a storm ultimately led to the end of the Opportunity rover's mission, as its solar panels were choked with dust, leaving it powerless. Even without rain or oceans, Mars remains an active and restless world. Europa may have a salty ocean beneath its ice. Beneath the frozen, icy shell of Jupiter's moon Europa, There is compelling evidence for the existence of a vast subsurface ocean of liquid water. The intense tidal forces exerted by Jupiter's immense gravity flex Europa's interior, generating heat that may be sufficient to keep the ocean from freezing solid. The surface of Europa is streaked with dark lines and ridges, telltale signs of shifting ice, and spacecraft have detected magnetic signatures and chemical traces that strongly support the ocean hypothesis. What makes Europa especially fascinating is the distinct possibility that this hidden sea could potentially harbor life. It's a dark alien ocean, warmed from below, sealed beneath a thick layer of ice, yet potentially rich with the ingredients necessary for biological processes to occur. Volcano taller than Everest. Olympus than Everest. Olympus Mons, the tallest volcano in the entire solar system, towers nearly 22 kilometers above the Martian plains, almost 3 times the height of Mount Everest, the highest point on Earth. It's so incredibly wide that it would cover the entire state of New Mexico. Formed by repeated eruptions over millions of years, Olympus Mons grew to such a massive size partly because Mars lacks the dynamic system of plate tectonics that we have on Earth. On Earth, volcanic hotspots shift over time as the plates move, creating chains of islands like Hawaii. But on Mars, the crust remains relatively stationary, allowing magma to erupt in the same location again and again. The result is a single massive shield volcano that looms silently in the Martian night. Saturn's rings are paper-thin. Saturn's majestic rings stretch for more than 280,000 kilometers across, yet they are astonishingly thin. In most places, the rings are less than 100 meters thick. That's thinner than many of the skyscrapers found in our cities here on Earth. Composed mostly of water ice, the ring particles range in size from tiny grains of dust to house-sized boulders. When sunlight passes through the ring plane edge-on, they nearly disappear from view like a sheet of glass turned sideways, becoming almost invisible. Their remarkable flatness is maintained by the planet's gravity, the self-organization of billions of icy fragments, and the subtle influence of small shepherd moons. From a distance, they appear solid and continuous, but up close, they're revealed to be delicate and ethereal. Earth is the densest planet. Of all the planets in our solar system, Earth is the densest. This means that it packs more mass into each cubic centimeter than any other planet, thanks to its composition of a metal-rich core and a silicate mantle. Earth's density is approximately 5 grams per cubic centimeter, higher than that of Jupiter despite the gas giant's far greater overall size. This high density plays a critical role in generating Earth's powerful magnetic field, which arises from the motion of molten iron within its outer core. Our planet's internal structure is compact, heavy, and distinctly layered, shaping not just its gravity but its geology, its ability to protect itself from the harsh environment of space. The sun vibrates like a musical instrument. Though we can't hear it with our ears, the sun constantly rings with pressure waves that ripple through its blazing layers. These oscillations, caused by rising and falling currents of plasma, generate ultra-low frequency sounds that are far below the range of human hearing. Scientists study these vibrations through a technique called helioseismology. By meticulously tracking how these waves travel and bounce within the sun's body, researchers can map its internal structure, much like geologists use seismic waves to explore Earth's interior. These solar songs reveal hidden flows, magnetic activity, and the intricate dynamics of fusion deep within the core. In a way, the sun is always humming, quietly revealing its secrets through vibration and rhythm. Venus rotates backward. Like most planets in our solar system, Venus spins in the opposite direction, a phenomenon known as retrograde rotation. On Venus, the sun rises in the west and sets in the east, an inversion of what we experience here on Earth. Even stranger, its rotation is incredibly slow. A single day on Venus lasts longer than its year, taking 243 Earth days to complete one rotation. Scientists aren't entirely certain why this happened, but one prevailing hypothesis suggests a massive collision early in its history may have altered its spin. Another theory proposes that tidal interactions with the sun slowly flipped its axis over vast stretches of time. Whatever the underlying cause, Venus stands alone as a slow-turning world with a reversed rhythm. Jupiter has more than 90 moons. The gas giant Jupiter is not just the largest planet in our solar system, it's also the undisputed king of moons. As of now, astronomers have identified over 90 natural satellites orbiting it, and new ones are still being discovered with regularity. Its four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named in honor of Galileo Galilei, who first observed them through his telescope in 1610, forever changing our understanding of the cosmos. But beyond these four giants lies a swarm of smaller, irregular moons, many of which were likely captured from passing objects. Some of them orbit in a retrograde direction, some are only a few kilometers across. Together, a miniature solar system in orbit around Jupiter, bound by the planet's immense gravity and its tumultuous history. Mercury hides ice in its shadows. Scorching hot during the day and freezing cold at night, Mercury is probably the last place you'd expect to find ice. Yet some radar have confirmed the presence of these bright icy patches. Scientists believe the water may have arrived from comet impacts or ancient volcanic outgassing. It may be the way even in reality. The rest are scattered fragments from the early solar system, ancient building blocks that never quite coalesced into a full-fledged planet. Uranus rolls around the sun. Most planets spin like tops, tilted slightly on their axis. But Uranus is tipped so far over that it essentially rolls along its orbital path with an axial tilt of 98 degrees. This means that its poles point almost directly at the sun during parts of its orbit, giving it extreme and bizarre seasons. But Uranus is tipped so far over that it essentially rolls along its orbital path with an axial tilt of 98 degrees. This means that its poles point almost directly at the sun during parts of its orbit, giving it extreme and bizarre seasons. Each pole experiences 42 years of continuous daylight, followed by 42 years of total darkness. The cause of this extreme tilt is still debated, but knocked sideways by a massive collision long ago. Uranus's tilted orientation gives it one of the strangest climates in the entire solar system. Jupiter's radiation belts are deadly. Jupiter is surrounded by a massive magnetic field, the strongest of any planet in our solar system, and within it are radiation belts so intense that they would destroy unprotected spacecraft in a matter of hours. These belts are filled with charged particles trapped by the planet's magnetic field, forming zones of high-energy radiation similar to Earth's Van Allen belts, but vastly more powerful. These belts are filled with charged particles trapped by the planet's magnetic field, forming zones of high-energy radiation similar to Earth's Van Allen belts, but vastly more powerful. Jupiter's largest moons are also exposed to this intense radiation, which can affect their surfaces and potential habitability. To survive in orbit around Jupiter, spacecraft must take special shielding measures or remain in low radiation pathways. It's a beautiful world, but one that's wrapped in invisible danger. The Sun contains nearly all the mass in the solar system. At the heart of our solar system, the Sun dominates not just with its light and gravity, but with sheer mass. It holds over 99.8% of all the mass in the solar system. That means that everything else, all the planets, moons, asteroids, comets, and dust, makes up less than 0.25%. Its gravitational pull binds everything in orbit, from tiny grains in the asteroid belt to distant comets in the Oort cloud. This immense mass is what fuels the fusion reactions at its core, converting hydrogen into helium and flooding space with the energy of day. There are more dwarf planets than classical planets. Beyond Neptune lies a scattered population of icy, distant objects, many of which are large enough to qualify as dwarf planets. Pluto is the most famous example, but it's just one among many. Others like Eris, Haumea, and Makemake share this status, and more candidates are constantly being discovered in the Kuiper Belt and beyond. In fact, the number of dwarf planets may vastly exceed that of the 8 classical planets. These small, round worlds are relics of the early solar system, untouched and ancient. Though they orbit in the cold shadows, they hold crucial clues to the formation of everything we know. A day on Venus lasts longer than its year. Venus has one of the slowest rotations of any planet. It takes 243 Earth days to spin once on its axis. Meanwhile, it only takes 225 days to complete one orbit around the Sun. That means a single day on Venus, from one sunrise to the next, is actually longer than a full year. This sluggish spin also contributes to extreme surface conditions, with temperatures hot enough to melt lead. Combined with its thick acidic atmosphere and crushing pressure, Venus is a world of slow, simmering heat and eerie, sunless days. Titan has lakes made of methane. Saturn's largest moon, Titan, is the only other place in our solar system known to have stable liquids on its surface. But unlike Earth, these aren't made of water. Instead, Titan's lakes and rivers consist of liquid methane and ethane flowing across a landscape sculpted by cold chemistry. Its thick atmosphere, rich in nitrogen, forms weather systems that include methane rain and even seasonal storms. Some of Titan's lakes are vast, stretching for hundreds of kilometers. Beneath the icy surface, scientists believe a subsurface ocean of water may also exist. Titan is a world with familiar shapes, clouds, rivers, coasts, built from alien substances. The moons of Mars may be captured asteroids. Mars has two tiny, misshapen moons, Phobos and Deimos. They look more like asteroids than traditional moons, irregular, rocky, and pockmarked with craters. Many scientists believe they were once part of the asteroid belt and were captured by Mars's gravity long ago. Their strange orbits and low densities support this idea, though some alternative theories suggest they may have formed from debris after a massive impact. Phobos is slowly spiraling toward Mars and will eventually break apart or crash into the planet. Deimos is drifting away. These little moons are quiet passengers in orbit, remnants of a chaotic past. Jupiter glows with its own heat. Like most planets, Jupiter gives off more energy than it receives from the Sun. This internal glow comes from leftover heat from its formation, a kind of gravitational energy released when the planet's immense mass collapsed together. For time, it continues to contract slightly, generating heat in the process. This warmth drives Jupiter's turbulent weather systems, including its giant storms and swirling bands. In the infrared spectrum, Jupiter shines brightly like a smoldering coal beneath its cloud layers. It's not a star, but it almost became one. If it had been just a bit more massive, it could have ignited into a failed sun. Neptune was discovered through math. Unlike other planets, Neptune wasn't discovered by simply looking through a telescope. Instead, astronomers noticed irregularities in Uranus's orbit, tiny deviations that couldn't be explained by known gravitational forces. Two mathematicians working independently in the 1840s used these strange motions to predict the location of a hidden planet. When astronomers pointed their telescopes toward the calculated position, Neptune was right there. It was a triumph of celestial mechanics, confirming that unseen forces could be mapped through mathematics alone. Neptune was the first planet found on paper before it was seen through glass, a world brought to light by numbers. Saturn's North Pole has a hexagon. At Saturn's North Pole, a massive cloud pattern spins in the shape of a nearly perfect hexagon. This six-sided jet stream spans over 30,000 kilometers across, wider than Earth, and has persisted for decades, possibly centuries. Scientists believe the hexagon forms from the way Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. Lab experiments, similar shapes appear when rotating fluids at different speeds. The fact that such a geometric shape can emerge naturally in a planetary atmosphere is still one of the more surreal and elegant phenomena in the solar system. The Sun's atmosphere is hotter than its surface. It might seem intuitive that the hottest part of the Sun would be its surface, but that's not the case. The visible surface, or photosphere, has a temperature of about 5,500 degrees Celsius, yet the outer atmosphere, known as the corona, can reach temperatures of over 1,000,000 degrees Celsius. This unexpected increase in temperature has puzzled scientists for decades. One theory suggests that magnetic waves from deep within the Sun transfer energy upward and heat the corona from below. Another possibility involves tiny solar explosions called nanoflares. Their way, the Sun's outer layers glow with mysterious searing heat far beyond their source. The Kuiper belt is full of icy worlds. Beyond Neptune lies a wide ring of icy objects known as the Kuiper belt. It stretches billions of kilometers from the Sun and is home to countless frozen bodies, including Pluto, Eris, Haumea, and Makemake. These aren't stars or planets, but ancient remnants from the solar system's formation. Some are spherical and classified as dwarf planets, while others are irregular, tumbling through space. The Kuiper belt is similar in structure to the asteroid belt, but it's far colder and contains more primordial ice. It's a fossil zone, a frozen archive of the materials that built the outer worlds. The Oort cloud may stretch a light year from the Sun. Far beyond the Kuiper belt, even beyond Pluto's furthest reach, lies a hypothetical shell of icy bodies known as the Oort cloud. Though never directly observed, this sphere of frozen debris is thought to encircle the solar system and extend nearly a way. It's it's the likely source of long-period which appear from the depths of space with orbits. These icy wanderers, born in the Oort cloud, offer us glimpses into the distant and ancient past of our solar system. These distant objects in the Oort cloud are only weakly gravitationally bound to the Sun, making them susceptible to the gravitational nudges of passing stars or the subtle tug of the galactic tide. Should such a perturbation occur, one of these icy bodies could be sent hurtling inwards towards the inner solar system, potentially becoming a long-period comet. If the Oort cloud truly exists, it delineates the true outer boundary of the Sun's gravitational influence, a vast and diffuse halo of icy wanderers silently orbiting at the edge of our solar system's domain. A moon of Jupiter holds the title of the most volcanically active world in our solar system. This Jovian moon is a seething, restless sphere perpetually tormented by intense geological activity. A moon of Jupiter holds the title of the most volcanically active world in our solar system. This Jovian moon is a seething, restless sphere perpetually tormented by intense geological activity. Its surface, a canvas of sulfurous compounds and molten rock, is constantly being reshaped by frequent and powerful volcanic eruptions. These eruptions paint the landscape in a vibrant palette of yellows, reds, and blacks, creating a surreal and ever-changing vista. Some of these volcanic plumes reach incredible heights, ascending hundreds of kilometers into space, a testament to the immense forces at play beneath Io's surface. The driving force behind this extreme volcanism is tidal heating. Io is subjected to a relentless gravitational tug-of-war, squeezed and stretched by the combined gravitational forces of Jupiter and its neighboring moons. Io is subjected to a relentless gravitational tug-of-war, squeezed and stretched by the combined gravitational forces of Jupiter and its neighboring moons. This constant flexing generates tremendous friction within Io's interior, heating the moon's mantle and powering its furious geological activity. This constant flexing generates tremendous friction within Io's interior, heating the moon's mantle and powering its furious geological activity. Unlike Earth, where the crust gradually cools over time, Io's surface remains perpetually young, volatile, and ever-changing, a true lavalit moon with a molten heart. Triton, Neptune's largest moon, displays a unique characteristic. It orbits its planet in the opposite direction of Neptune's rotation, a motion referred to as a retrograde orbit. Triton, Neptune's largest moon, displays a unique characteristic. It orbits its planet in the opposite direction of Neptune's rotation, a motion referred to as a retrograde orbit. This unusual trajectory strongly suggests that Triton did not form alongside Neptune but was likely captured from the Kuiper belt, a region beyond Neptune populated by icy bodies. This capture event may have triggered a period of dramatic upheaval within the Neptunian system, potentially disrupting Neptune's original satellite arrangement. Furthermore, Triton is geologically active, exhibiting cryovolcanoes that spew icy material into space and a thin atmosphere that waxes and wanes with the changing seasons. Cold, distant, and defying expectations at every turn, Triton stands as a truly unique and enigmatic world. Compared to the size of its host planet, Earth's moon is exceptionally large. In fact, no other rocky planet in our solar system boasts such a relatively large satellite. The moon's diameter is approximately 1/4 the diameter of Earth, a ratio more commonly observed in dwarf planet-moon systems than in systems involving full-sized planets. The moon's diameter is approximately 1/4 the diameter of Earth, a ratio more commonly observed in dwarf planet-moon systems than in systems involving full-sized planets. The prevailing scientific theory posits that the moon formed following a colossal impact between a Mars-sized object and the early Earth. This impact ejected vast amounts of debris into orbit, which subsequently coalesced to form the moon. The prevailing scientific theory posits that the moon formed following a colossal impact between a Mars-sized object and the early Earth. This impact ejected vast amounts of debris into orbit, which subsequently coalesced to form the Moon. This close partnership between Earth and its moon has profoundly influenced our planet's tides, climate, and overall stability over billions of years. Our moon is not merely a celestial companion, it is a cosmic legacy of a planetary collision and subsequent renewal. While we often visualize planets following perfect circular paths around the Sun, their actual orbits are elliptical. These ellipses are essentially slightly stretched circles, with the Sun positioned off-center. While we often visualize planets following perfect circular paths around the Sun, their actual orbits are elliptical. These ellipses are essentially slightly stretched circles, with the Sun positioned off-center. This elliptical shape causes each planet to have a point of closest approach to the Sun, known as perihelion, and a point of greatest distance, known as aphelion. For the majority of planets, the difference between these distances is subtle. This elliptical shape causes each planet to have a point of closest approach to the Sun, known as perihelion, and a point of greatest distance, known as aphelion. For the majority of planets, the difference between these distances is subtle. However, for others, such as Mercury and Pluto, the variation is much more pronounced. These variations influence the intensity of seasonal changes, the amount of solar radiation received, and the planet's orbital speed. However, for others, such as Mercury and Pluto, the variation is much more pronounced. These variations influence the intensity of seasonal changes, the amount of solar radiation received, and the planet's orbital speed. The elliptical nature of planetary motion was first elucidated by Johannes Kepler in the 1600s, revolutionizing our understanding of the solar system's elegant mechanics. Long-period comets, those celestial wanderers that make an appearance only once every few thousand years, are believed to originate from the Oort cloud, a hypothetical spherical shell of icy debris located nearly a light-year from the Sun. These comets travel along highly elongated, loosely bound orbits and are often dislodged from their distant resting places by the gravitational influences of passing stars or the galactic tide. These comets, after this white dwarf will no longer generate energy through nuclear fusion but will slowly cool over trillions of years. This will be the Sun's final form, a glowing ember fading in the darkness, marking the end of its stellar journey. Despite its colder temperatures and thinner atmosphere, Mars experiences seasons remarkably similar to those on Earth. This is primarily due to the fact that Mars has an axial tilt of approximately 25 degrees, comparable to Earth's 23-degree tilt. As Mars orbits the Sun, this axial tilt causes sunlight to strike different hemispheres more directly at different times of the year, resulting in a cycle of spring, summer, autumn, and winter, each characterized by varying temperatures and amounts of daylight. As Mars orbits the Sun, this axial tilt causes sunlight to strike different hemispheres more directly at different times of the year, resulting in a cycle of spring, summer, autumn, and winter, each characterized by varying temperatures and amounts of daylight. Martian seasons also influence the behavior of the polar ice caps, the frequency and intensity of dust storms, and even subtle fluctuations in atmospheric pressure. However, these seasons unfold at a slower pace than on Earth because Mars takes nearly twice as long to complete an orbit around the Sun. Ganymede, a moon of Jupiter, is the largest natural satellite in our solar system, even surpassing the planet Mercury in size. With a diameter exceeding 5,000 kilometers, Ganymede possesses a rocky core, a potential subsurface ocean, and a surface crust covered in grooved ice and ancient impact scars. With a diameter exceeding 5,000 kilometers, Ganymede possesses a rocky core, a potential subsurface ocean, and a surface crust covered in grooved ice and ancient impact scars. Equally, Ganymede is the only moon known to possess its own intrinsic magnetic field, which generates shimmering auroras in its thin atmosphere. Scientists speculate that Ganymede may harbor multiple layers of oceans sandwiched between sheets of ice, forming a complex and layered internal structure. Despite its immense size and fascinating internal composition, Ganymede remains a relatively quiet and dark world, orbiting deep within Jupiter's powerful magnetic field. Although Pluto is typically considered the most distant of the classical planets or dwarf planets, its orbit is highly elliptical. This means that at times Pluto ventures closer to the Sun than Neptune. This phenomenon last occurred between 1979 and 1999, during which period Pluto temporarily became the eighth planet from the Sun instead of the ninth. Despite this orbital crossover, Pluto and Neptune never collide or approach each other dangerously closely due to a phenomenon known as orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes precisely 2. This gravitational choreography maintains a stable dance between the two worlds, ensuring that their paths never intersect. It's a testament to the delicate balance governed by celestial rhythm and time. Roughly every 11 Earth years, the Sun's magnetic field undergoes a dramatic reversal. The north and south magnetic poles essentially switch places. This process, known as the solar magnetic cycle, is intricately linked to the Sun's internal dynamics and has a significant impact on solar activity, including the formation of sunspots, the eruption of solar flares, and the ejection of coronal mass ejections. During the peak of the cycle, referred to as solar maximum, the Sun exhibits heightened activity, characterized by more intense radiation and more frequent magnetic storms. As the cycle progresses towards its end, solar activity gradually declines, eventually reaching solar minimum. These cycles have a measurable influence on Earth's upper atmosphere, satellites in orbit, and even the occurrence of auroras. The Sun's magnetism is not static, but rather pulses and flows like a breathing magnetic heartbeat. The common belief that planetary alignments can trigger earthquakes, floods, or other major disasters on Earth is, in fact, a myth. There is no scientific evidence to support such claims. The gravitational pull exerted by other planets on Earth is minuscule compared to the gravitational influence of the Moon or the Sun. Even during rare planetary alignments, their combined gravitational effect remains negligible. The Moon, by virtue of its proximity to Earth, exerts a far greater influence on our planet's tides and seismic stress than the massive but distant planets such as Jupiter or Saturn. Planetary alignments are aesthetically pleasing and mathematically intriguing, but they are gravitationally harmless. They are simply a silent dance of distant worlds, not a harbinger of celestial doom. To escape the gravitational grasp of the Sun and venture into interstellar space is no small feat. The Voyager 1 and Voyager 2 spacecraft, launched in the 1970s, have only recently entered interstellar space, the region beyond the heliopause where the influence of the interstellar medium begins to dominate. These missions required more than 40 years to reach this boundary, traveling outwards at speeds exceeding 60,000 kilometers per hour. The Voyager probes have traversed the orbits of all the planets, passed through the Kuiper Belt, and continued their journey into the darkness beyond. They carry instruments that are still functioning, as well as a golden record filled with sounds and images of Earth. They serve as our silent ambassadors to the galaxy, carrying a message from humanity to the cosmos. Surrounding our planet is an invisible magnetic field, generated by the movement of molten iron within Earth's outer core. This magnetic field deflects charged particles emanating from the Sun, effectively shielding our atmosphere and surface from harmful solar and cosmic radiation. Without this magnetic shield, the solar wind would gradually erode our atmosphere, as is believed to have occurred on Mars. Without this magnetic shield, the solar wind would gradually erode our atmosphere, as is believed to have occurred on Mars. The magnetic field also funnels some of these charged particles towards the poles, where they interact with atmospheric gases to produce the mesmerizing auroras, shimmering curtains of green, red, and violet light. Earth's magnetosphere serves as a dynamic shield, playing a crucial role in preserving both life and climate over geological timescales. Each year, the Moon drifts approximately 3.8 centimeters farther away from Earth. This gradual retreat is caused by tidal interactions between the two bodies. The gravitational pull between Earth and the Moon creates bulges in our planet's oceans, which in turn exert a slight gravitational force on the Moon, pushing it slightly outwards. In the distant past, the Moon was significantly closer to Earth and appeared much larger in the sky. As the Moon continues to recede, our days will gradually lengthen and solar eclipses will become less frequent and dramatic. Billions of years from now, the Moon's orbit will be so wide that total solar eclipses will no longer be possible. The sky is constantly changing, even if we cannot yet perceive those changes directly. Far beyond Neptune lies the Kuiper Belt, a region teeming with not only dwarf planets but also smaller icy bodies, some of which possess startlingly bright surfaces. Haumea, for example, is a fast-spinning, football-shaped object coated in crystalline water ice, giving it a highly reflective surface. Eris, another Kuiper belt object, reflects nearly all of the sunlight that strikes it, making it one of the most reflective bodies in the solar system, even brighter than freshly fallen snow. These objects may have been resurfaced by cryovolcanism, impacts, or other chemical interactions. The darkness at the edge of the sun's reach, some of its distant worlds gleam like cold mirrors, reflecting faint sunlight in their frozen silence. Saturn's tiny moon Enceladus may be diminutive in size, but it conceals a spectacular secret beneath its icy surface. From its south pole, towering geysers of water vapor and ice crystals erupt into space through cracks known as tiger stripes. These plumes are powered by tidal heating within the moon's interior, where friction generated by Saturn's gravitational pull keeps a subsurface ocean in a liquid state. The material contained within these plumes includes organic compounds, salts, and even evidence of hydrothermal activity, raising the tantalizing possibility of life. Some of the water escapes into space and helps replenish Saturn's E-ring, creating a living connection between moon and planet. Not all asteroids are composed of solid rock. Many are, in fact, loose collections of stones, gravel, and dust held together only by their mutual gravitational attraction. These structures are known as rubble piles. Such fragile bodies can form after collisions shatter larger asteroids, with the resulting debris slowly coalescing back together over time. Rubble pile asteroids can possess large internal voids, exhibit strange rotational behaviors, and even change shape under pressure. Missions such as Hayabusa 2 and OSIRIS-REx have visited such bodies, confirming their delicate and porous nature. These asteroids are not monolithic relics, but rather chaotic assemblages, ancient and drifting ruins of early planetary construction that barely manage to hold themselves together as they orbit the Sun. Mercury, despite its small size, possesses an unusually large iron core. This metallic core accounts for approximately 80% of the planet's radius, a far greater proportion than that observed in Earth or Venus. The reason for this oversized core remains a subject of scientific debate. Some scientists hypothesize that Mercury may have once possessed a thick rocky mantle that was subsequently stripped away by a giant impact. Others believe that the planet formed close to the Sun, where solar forces favored the accumulation of heavier elements. The result is a planet with a thin crust, a huge core, and a weak magnetic field, a metal-heavy survivor from the solar system's chaotic youth. Among the rocky planets, only Mercury and Venus lack natural satellites. While Mercury's proximity to the Sun may explain its lack of moons, Venus's situation is more puzzling. It is roughly the same size as Earth, which possesses a large moon, yet Venus has none. Some theories suggest that Venus may have once had a moon that either fell back into the planet or was lost as a result of a collision. Others propose that Venus's slow retrograde rotation might prevent stable orbits from forming. Whatever the underlying cause, Venus orbits the Sun alone, a bright cloud-enshrouded world with no lunar companion's twilight sky. While Earth has just one moon, and Mars has two tiny ones, the giant planets of the outer solar system are surrounded by sprawling systems of satellites. Jupiter and Saturn each boast dozens of confirmed moons, ranging in size from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host numerous icy moons, some with complex orbits and hidden subsurface oceans. Jupiter and Saturn each boast dozens of confirmed moons, ranging in size from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host numerous icy moons, some with complex orbits and hidden subsurface oceans. These gas giants act as miniature solar systems in their own right, their gravity drawing in debris and facilitating the coalescence of satellites over time. The farther one ventures from the Sun, the more moons one is likely to find, a testament to the power of gravity to gather companions in the cold depths of space. The Hubble Space Telescope, despite orbiting just above Earth, has captured detailed images of the outer planets, including the cloud bands on Jupiter, storms on Neptune, and seasonal changes on Mars. Hubble's exceptional clarity enables scientists to track the development of storms, monitor impact events, and study planetary atmospheres in ultraviolet and visible light. Hubble's exceptional clarity enables scientists to track the development of storms, monitor impact events, and study planetary atmospheres in ultraviolet and visible light. From its quiet vantage point in low Earth orbit, Hubble observes not only the distant galaxies but also the ever-changing faces of our neighboring worlds. Jupiter's Great Red Spot is a colossal storm raging in the planet's southern hemisphere, large enough to engulf 2 or even 3 Earths. It has been swirling for at least 350 years, and possibly much longer. First observed in the 1600s through early telescopes, the storm has undergone changes over time, gradually shrinking in size but still remaining incredibly powerful. Its distinctive reddish hue is thought to be caused by complex chemical reactions occurring in Jupiter's atmosphere, triggered by sunlight and high-altitude compounds. Wind speeds along its outer edges can exceed 400 kilometers per hour. While storms on Earth typically last for days or weeks, this Jovian tempest has persisted for centuries, trapped within the planet's turbulent belts. Although Neptune lies far from the Sun, it is not a frozen and inert world. In fact, Neptune radiates approximately 2 times more energy than it receives from the Sun. This internal heat drives strong winds and powerful storm systems, including some of the fastest winds ever recorded in the solar system. The precise source of Neptune's internal heat remains uncertain, but potential explanations include residual energy from its formation, slow gravitational contraction, or radioactive decay within its core. Despite its extreme distance from the Sun, Neptune is a world of surprising energy, a planet with a cold exterior and a warm, restless interior, constantly reshaping its windswept atmosphere. Our planet is unique in that water exists naturally on its surface in all 3 states: solid, liquid, and gas. Ice caps and glaciers, oceans and lakes, clouds and water vapor all coexist and cycle through the atmosphere, land, and sea. This delicate balance is crucial for the sustenance of life on Earth and is regulated by our planet's distance from the Sun, its atmospheric pressure, and its relatively stable climate. Other worlds may have water in isolated forms such as icy crusts, water vapor in thin atmospheres, or hidden subsurface oceans, but none exhibit the same dynamic planet-wide presence of water as Earth. On Earth, water flows, freezes, and evaporates in a never-ending, life-sustaining dance. As the solar wind flows outwards from the Sun, it eventually collides with the interstellar medium, the thin gas and dust that permeates space between stars. This boundary is known as the heliopause, and it defines the outer edge of the Sun's protective bubble, called the heliosphere. Beyond this point, the pressure exerted by other stars and galactic particles becomes stronger than the force of the solar wind. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, marking their entry into true interstellar space. While the Sun's gravitational influence extends much farther, the heliopause marks the end of its energetic reach, the final vestige of our influence before the vastness of deep space begins. Our entire solar system is currently moving through a region of space known as the local interstellar cloud, a relatively thin concentration of gas and dust approximately 30 light-years across. This cloud is, in turn, part of a larger structure called the local bubble, which was likely formed by ancient supernova explosions. As the Sun traverses this cloud at a speed of approximately 7,000 kilometers per hour, its heliosphere acts as a shield, deflecting interstellar material. Scientists study this cloud to better understand how interstellar conditions can affect cosmic rays, the shape of the heliosphere, and even Earth's climate. We are not stationary in space. We are slowly and silently sailing through a galactic fog. Geological activity is not limited solely to planets. Several moons in the solar system also exhibit signs of internal energy and surface change. A moon of Jupiter is riddled with active volcanoes fueled by tidal heating. Enceladus, orbiting Saturn, vents plumes of water vapor into space through fractures in its icy surface. Europa and Ganymede are believed to possess subsurface oceans stirred by internal warmth. Even distant Triton, Neptune's captured moon, shows evidence of cryovolcanism, icy eruptions driven by shifting pressures beneath its surface. These moons are not simply static ice balls. They are restless worlds with active geology, fascinating chemistry, and perhaps even the potential for life hidden beneath their frozen exteriors. Although Pluto is small and cold, it possesses a thin atmosphere composed primarily of nitrogen with trace amounts of methane and carbon monoxide. When Pluto approaches the Sun during its elliptical orbit, Surface ices sublimate into gas, forming a hazy envelope that expands into space. However, as Pluto moves farther away from the Sun, the atmosphere cools and collapses, freezing back onto the surface like. This cycle repeats the course of Pluto's 248-year orbit. During the New Horizons flyby in 2015, Pluto's atmosphere was visible as a layered blue haze, a fleeting breath of warmth around a world that spends the vast majority of its time in deep cosmic winter. Deep within the Sun, at its very center, temperatures soar to over 50 million degrees Celsius. At these extreme temperatures and pressures, hydrogen atoms are compressed to the point where they fuse together to form helium, releasing enormous amounts of energy in the process. This nuclear fusion is what powers the Sun's light and heat, and ultimately all life on Earth. The energy generated in the core takes hundreds of thousands of years to reach the Sun's surface, bouncing through layers of dense plasma. Once it escapes, it travels across space in just over 8 minutes to reach us. The energy generated in the core takes hundreds of thousands of years to reach the Sun's surface, bouncing through layers of dense plasma. Once it escapes, it travels across space in just over 8 minutes to reach us. The Sun's seemingly calm and radiant exterior belies the unimaginably hot and violent processes occurring within its core. While Saturn's rings are undoubtedly the most iconic, Uranus also possesses a ring system. Uranus has 13 known rings, though they are much darker and fainter than Saturn's. The Sun's seemingly calm and radiant exterior belies the unimaginably hot and violent processes occurring within its core. While Saturn's rings are undoubtedly the most iconic, Uranus also possesses a ring system. Uranus has 13 known rings, though they are much darker and fainter than Saturn's. Composed of tiny particles of rock and ice, these rings orbit in alignment with Uranus's unusual tilt. Since the planet lies almost on its side, the rings appear vertical when viewed from above the Sun's north pole. Some of the rings are narrow and sharply defined, likely shaped by small shepherd moons that help to maintain their structure. The rings were not discovered until 1977 when they were observed to block the light of a background star. These subtle, shadowy bands circle a planet that is tilted on its side. The solar wind, a continuous stream of charged particles emitted by the Sun, flows outwards in all directions, creating a vast magnetic bubble around the entire solar system. This structure is known as the heliosphere, and it acts as a shield against galactic radiation. Shaped by solar activity and interstellar pressure, the heliosphere extends far beyond Pluto, encompassing the planets, comets, and other distant objects. Its outer edge, the heliopause, marks the point where the Sun's influence fades. As the Sun orbits the Milky Way galaxy, the heliosphere moves along with it, protecting the solar system as it drifts through ever-changing regions of interstellar space. For centuries, astronomers noticed a peculiar anomaly in Mercury's orbit. Its point of closest approach to the Sun, known as perihelion, slowly shifted over time, more than could be accounted for by Newtonian physics. 1915, Albert Einstein's theory of general relativity provided a solution to this long-standing puzzle. According to general relativity, massive objects like the Sun warp the fabric of space-time, subtly altering the paths of orbiting planets. The small but measurable effect on Mercury's orbit precisely matched Einstein's predictions. This became one of the first experimental confirmations of his revolutionary theory and a resounding triumph of mathematics, explaining a seemingly insignificant quirk in the motion of a scorched and rocky world. The daily rise and fall of ocean tides on Earth are primarily caused by the gravitational pull of the Moon. As the Moon's gravity tugs on Earth's oceans, it creates bulges on the side of the planet facing the Moon and on the opposite side. As Earth rotates, these bulges move across the globe, resulting in high and low tides. The Sun also influences tides, creating spring and neap tides depending on its alignment with the Moon. As Earth rotates, these bulges move across the globe, resulting in high and low tides. The Sun also influences tides, creating spring and neap tides depending on its alignment with the Moon. Tidal forces not only affect oceans but can also subtly shift the Earth's crust and even influence the planet's rotation. The Moon's silent pull keeps the oceans in constant motion. Astronomers have observed that some distant objects in the Kuiper Belt follow clustered, elongated orbits that cannot be easily explained by the gravitational influence of the known planets. leading theory proposes the existence of a large, as yet undetected planet, sometimes referred to as Planet 9, which may be influencing these distant orbits with its gravity. If it exists, this hidden planet would be several times the mass of Earth and would orbit far beyond Pluto, taking thousands of years to complete a single revolution around the Sun. While no direct evidence has yet confirmed its existence, telescopes are actively searching for it. If Planet 9 is ultimately discovered, it would reshape our understanding of the solar system's outer architecture. Jupiter's moon Callisto appears to be a quiet and heavily cratered world, with an ancient surface untouched by recent geological activity. However, deep beneath its frozen crust, scientists suspect that a subsurface ocean may exist, kept liquid by internal heating and potentially by residual heat left over from its formation. This hidden ocean remains a tantalizing mystery, hinting at the possibility of liquid water and perhaps even the potential for life beneath the cold and icy surface of Callisto. Magnetic. If this, while Venus, the thick reflective clouds may bounce sunlight back into space, but they also act as a blanket, preventing precious heat from escaping. Mercury, on the other hand, possesses only a tenuous exosphere, offering virtually no insulation and allowing it to cool rapidly on its dark side. Venus's fiery fate isn't solely dictated by proximity to the Sun. It's a stark testament to the power of atmospheric composition and trapped radiation. Saturn's rings, a breathtaking spectacle, are composed primarily of ice. Venus's fiery fate isn't solely dictated by proximity to the Sun. It's a stark testament to the power of atmospheric composition and trapped radiation. Saturn's rings, a breathtaking spectacle, are composed primarily of ice. Though they appear from afar as solid shimmering bands, Saturn's rings are actually composed of countless individual particles, primarily water ice, ranging in size from minuscule grains of dust to chunks as large as houses. These icy fragments orbit Saturn in an incredibly thin, flat disk, meticulously kept in place by the planet's powerful gravity and the subtle influences of nearby moons. The ice crystals provide the rings with their remarkable reflectivity, making them one of the most brilliant features in our solar system when viewed from afar. Embedded within the rings are narrow gaps, intricate wave patterns, and delicate ringlets, all shaped by gravitational resonances. The rings are a dynamic, ever-changing structure sculpted by the constant motion of icy particles caught in a celestial dance. Ceres, a fascinating hybrid, exists as both an asteroid and a dwarf planet. Located within the asteroid belt between Mars and Jupiter, Ceres is the largest object residing in that region, so large in fact that it meets the criteria to be classified as a dwarf planet. Discovered back in 1801, Ceres stands out from smaller, irregularly shaped asteroids due to its spherical form, hinting at a more complex internal structure. Some scientists theorize that it may even harbor a subsurface layer of briny water or mud. Data gathered by NASA's Dawn spacecraft revealed mysterious bright spots scattered across its surface, which were later identified as deposits of salt, likely remnants left behind by evaporating water. Ceres represents a fascinating hybrid world, neither entirely planet nor typical asteroid, offering a valuable glimpse into the early building blocks of planetary formation. Mars, the red planet, owes its distinctive color to rust. The surface of Mars is blanketed in a fine layer of iron oxide dust, the same compound responsible for the reddish-brown hue of rust. Over billions of years, this iron-rich material has undergone oxidation within the thin Martian atmosphere, giving rise to the planet's signature reddish appearance. The pervasive dust even tints the Martian sky during storms and coats the entire planet in a rusty veneer. Despite its overall rusty complexion, Mars also displays darker basaltic plains and gleaming polar ice caps, introducing subtle color variations across its surface. However, from a distance, that distinctive reddish tone dominates, a dusty beacon signaling oxidation on a cold desert world. Sunspots, enigmatic blemishes, are cooler regions on the Sun's surface. Though the Sun's surface blazes with temperatures reaching thousands of degrees, certain areas appear darker than their surroundings, not because they are cold, but because they are relatively cooler. These darker regions are known as sunspots, temporary areas where intense magnetic activity suppresses the outward flow of heat from the Sun's interior. Sunspots can grow to be larger than Earth and often appear in pairs or clusters. They follow a roughly 11-year cycle, increasing in number and activity as the sun approaches its solar maximum. Despite being referred to as spots, they are still incredibly hot, reaching temperatures of thousands of degrees, but the contrast with the even hotter surrounding areas makes them appear dark. Think of them as magnetic scars, revealing the sun's ever-changing internal dynamics. Despite being referred to as spots, they are still incredibly hot, reaching temperatures of thousands of degrees, but the contrast with the even hotter surrounding areas makes them appear dark. Think of them as magnetic scars, revealing the sun's ever-changing internal dynamics. Uranus, the sideways planet, was discovered with a telescope. Unlike the planets visible to the naked eye since ancient times, Uranus wasn't officially identified as a planet until 1781, when astronomer William Herschel observed it through a telescope. Initially, he mistook it for a comet or a star, but further observations confirmed its planetary motion. Uranus became the first planet discovered in the modern era, expanding the known boundaries of our solar system. Its discovery marked a shift from simple observation to instrument-based exploration. Since its discovery, Uranus has revealed many surprises, from its extreme axial tilt, essentially spinning on its side, to its faint rings and icy moons. It's a planet that quietly rewrote the map of the night sky. The solar system, a cosmic senior citizen, is approximately 46 billion years old. By meticulously studying ancient meteorites, analyzing radioactive isotopes, and examining the oldest rocks found on Earth and the Moon, scientists have pinpointed the age of the solar system to around 4.6 billion years. All began as a swirling cloud of gas and dust, a solar nebula that collapsed under its own gravity, eventually igniting to form the sun at its center. The remaining material gradually coalesced to form planets, moons, asteroids, and comets. This process of accretion and differentiation laid the foundation for everything that followed. The planets we observe today are survivors of a chaotic beginning, shaped by collisions, migrations, and long, slow cooling processes. This process of accretion and differentiation laid the foundation for everything that followed. The planets we observe today are survivors of a chaotic beginning, shaped by collisions, migrations, and long, slow cooling processes. Vesta, an asteroid with a planetary heart, possesses a layered structure. Vesta, the second largest object in the asteroid belt, is not merely a solid chunk of rock. It's a protoplanet that developed differentiated layers. Beneath its surface lies a mantle and a dense metallic core, remarkably similar to the internal structure of Earth and other terrestrial planets. This implies that Vesta once possessed enough internal heat to melt and separate into distinct layers, a process known as planetary differentiation. The massive impact that carved out the Rhea Silvia crater at its south pole may have even exposed some of these deeper layers. Vesta represents a frozen fossil, a planetary building block that never quite achieved full planet status, but provides a precious glimpse into planetary formation. The Moon, our silent companion, experiences moonquakes. Though it appears serene and motionless, the Moon occasionally trembles. These moonquakes can be triggered by tidal forces exerted by Earth's gravity, thermal expansion and contraction as the lunar surface heats and cools, or even by meteorite impacts. Some moonquakes originate deep within the lunar interior and can persist for up to an hour, significantly longer than typical earthquakes on Earth. Data collected during the Apollo missions first revealed these subtle tremors, and modern instruments continue to study them. While the Moon lacks tectonic plates, its quakes suggest an interior that is not entirely dormant. It's a solid world with a quiet, pulsing heart. Triton, a captured moon, defies expectations. While the Moon lacks tectonic plates, its quakes suggest an interior that is not entirely dormant. It's a solid world with a quiet, pulsing heart. Triton, a captured moon, defies expectations. Neptune's largest moon, Triton, stands out amongst major moons because of its retrograde orbit, orbiting Neptune in the opposite direction of the planet's rotation. This unusual orbital path suggests that Triton didn't form around Neptune, but was captured from the Kuiper Belt long ago. The gravitational disruption resulting from this capture may have shattered Neptune's original moons and possibly altered Triton's own interior, causing tidal heating. Today, Neptune, most of these moons are icy and dark, reflecting very little sunlight. Their orbits provide valuable clues about Neptune's tumultuous past and potential planetary migrations. Together, launched in 2018, NASA's Parker Solar Probe is the first spacecraft to directly venture into the Sun's outer atmosphere, known as the corona. It traverses this extreme environment at extraordinary speeds, faster than any human-made object, and endures temperatures exceeding 1,000 degrees Celsius, 1,800 degrees Fahrenheit. It traverses this extreme environment at extraordinary speeds, faster than any human-made object, and endures temperatures exceeding 1,000 degrees Celsius, 1,800 degrees Fahrenheit. Protected by a cutting-edge carbon composite heat shield, the probe dips closer to the Sun with each orbit, collecting data on solar wind, magnetic fields, and energetic particles. Protected by a cutting-edge carbon composite heat shield, the probe dips closer to the Sun with each orbit, collecting data on solar wind, magnetic fields, and energetic particles. Its primary mission is to unravel long-standing mysteries, such as why the corona is hotter than the Sun's surface and how solar flares accelerate. In a sense, it's not just studying the Sun, it's flying directly through it. Martian meteorites, wanderers from another world, have landed on Earth. Though Mars lies millions of kilometers away, fragments of it have actually landed on Earth. These Martian meteorites are pieces of rock that were ejected from the Martian surface by powerful asteroid impacts. These fragments traveled through space and eventually entered our atmosphere. Scientists can identify them by comparing their chemical composition to data collected by Mars rovers and orbiters. Some of these meteorites contain tiny bubbles of trapped Martian air and minerals shaped by water, providing direct evidence of Mars's geological and chemical history. These wayward stones represent samples from another world, sent to us by nature long before any spacecraft returned the favor. The Sun, a giant ball of gas, is primarily composed of hydrogen and helium. Approximately 70% of the Sun's mass is hydrogen, with helium making up most of the remainder. These two lightest elements dominate its composition and fuel the nuclear fusion reactions at its core. Under immense pressure and heat, hydrogen atoms fuse together to form helium, releasing vast amounts of energy in the process. The remaining 1 to 2% of the Sun's mass includes oxygen, carbon, nitrogen, and heavier elements, all of which originated in earlier generations of stars. Despite its brilliance and complexity, the Sun's composition is fundamentally simple: a glowing sphere of primordial gases by gravity and nuclear fire. Earth's axial tilt, the reason for the seasons, our world. Earth's axis is tilted at approximately 53.5 degrees relative to its orbit around the Sun. This tilt is the sole reason we experience the distinct seasons. When one hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences longer days, resulting in summer. Conversely, when that hemisphere is tilted away from the sunlight is weaker and the days are shorter, ushering in winter. Without this axial tilt, the seasons would be barely noticeable, and most of Earth's climates would be far more uniform. The tilt has shifted slightly over time due to gravitational influences from the Moon and other planets, but it remains a key factor in shaping life's seasonal rhythms. Jupiter's magnetosphere, a colossal presence, is the largest structure in the solar system. Jupiter's immense magnetic field extends millions of kilometers into space, creating a magnetosphere so vast that it would appear larger than the Sun in the night sky if it were visible to the naked eye. This field is generated by electric currents within the planet's metallic hydrogen interior. Within the magnetosphere, charged particles spiral along magnetic field lines, creating intense radiation belts, spectacular auroras, and powerful electrical storms. The field also captures particles from Io's volcanic eruptions and shapes the orbits of nearby moons. For spacecraft, the radiation levels within the magnetosphere pose a significant hazard. For scientists, it represents a natural laboratory for studying planetary magnetism at its most extreme. Planetary rings, shimmering but transient, may be temporary phenomena. Although they appear timeless and permanent, planetary rings, such as those encircling Saturn, Jupiter, Uranus, and Neptune, may be relatively short-lived on cosmic timescales. Rings typically form from shattered moons, leftover debris, or icy particles drawn into orbit. However, over millions of years, these materials can gradually spiral inward due to gravitational interactions, magnetic drag, or collisions, eventually falling onto the host planet. Observations suggest that Saturn's iconic rings may be less than 100 million years old and could vanish within another 100 million years. The rings we admire today might be a fleeting phase, a spectacular shimmering moment in a planet's much longer lifespan. The Moon's surface, a geological time capsule, barely changes over time. Without the effects of wind, rain, or active geological processes, the lunar surface remains almost entirely unchanged for millions, even billions of years. Footprints left by Apollo astronauts are likely to remain preserved for thousands of generations. Micrometeorites and cosmic radiation are the primary forces that slowly erode the lunar landscape, causing a gradual weathering known as space weathering. Craters formed by ancient impacts still dominate the terrain, providing a record of collisions that dates back to the solar system's earliest days. The Moon is not only Earth's closest neighbor, but also one of its oldest and most faithful geological archives. Icy moons, potential havens for life, may possess hydrothermal vents. Icy moons, potential havens for life, may possess hydrothermal vents. Beneath the icy crusts of moons like Europa and Enceladus, scientists hypothesize that subsurface oceans may come into contact with hot, rocky cores, potentially forming hydrothermal vents similar to those found on Earth's ocean floor. On our planet, such vents sustain entire ecosystems without sunlight, utilizing chemical energy derived from minerals and heated water. If similar vents exist on these icy moons, they could provide the necessary conditions for life: water, heat, and a constant source of energy. Plumes erupting from Enceladus even contain compounds associated with biological processes. These hidden underwater worlds may represent the most promising locations for the search for life beyond Earth. Sunlight's journey, a cosmic commute, takes over 8 minutes to reach Earth. The light that warms your skin and illuminates the sky began its journey in the sun's core, where nuclear fusion creates photons. These photons then embark on a long and arduous journey, taking hundreds of thousands of years to travel from the sun's center to its surface, bouncing and scattering through dense plasma. Once they finally escape the surface, however, they traverse the remaining distance to Earth, approximately 150 million kilometers, 93 million miles, in just over 8 minutes. When you witness a sunrise or gaze at the midday sun, you're seeing it not as it is, but as it was 8 minutes ago, a glimpse into the very recent past. Europa's cracked ice, dynamic surface, may shift like tectonic plates. The surface of Jupiter's moon. Europa is encased in a shell of ice crisscrossing ridges and chaotic terrain. These features suggest that the ice may be moving, breaking, sliding, and even subducting, similar to Earth's tectonic plates. If this hypothesis proves to be true, Europa would be the only known celestial body besides Earth exhibiting active plate-like motion. This process could facilitate the exchange of nutrients between the surface and the ocean below, potentially enhancing the moon's habitability. The driving force behind this activity is likely tidal flexing caused by Jupiter's immense gravity, which continually kneads Europa's interior. It's a frozen world, but far from a static one. Saturn, the buoyant giant, is less dense than water. If you could somehow place Saturn in a colossal cosmic bathtub, it would float. Not because it's hollow, but because its average density is less than that of water. Saturn is primarily composed of hydrogen and helium, which gives it a surprisingly low density despite its enormous size. Its volume is staggering, more than 700 times that of Earth, but its mass is only about 95 times greater. This low density imparts a gentle, diffuse structure to Saturn, coupled with rapid rotation that flattens it at the poles and bulges it at the equator. It's a giant of gas softly puffed into shape by gravity and motion. Solar flares, powerful eruptions, can disrupt technology on Earth. Solar flares are sudden and intense bursts of energy from the sun's surface, often associated with sunspot activity. These outbursts unleash vast amounts of radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. When these flares are directed toward Earth, they can disrupt the upper atmosphere, causing disturbances in GPS systems, radio communications, and satellite operations. In extreme cases, they can trigger geomagnetic storms that have the potential to damage power grids. While Earth's magnetic field offers some protection, solar flares serve as a reminder that the sun is not a steady light bulb but a dynamic and volatile star, one that occasionally sends ripples of energy pulsing across the solar system. The solar cycle, a celestial rhythm, influences auroras. While Earth's magnetic field offers some protection, solar flares serve as a reminder that the sun is not a steady light bulb but a dynamic and volatile star, one that occasionally sends ripples of energy pulsing across the solar system. The solar cycle, a celestial rhythm, influences auroras. Auroras, the shimmering curtains of green, red, and violet light that dance near Earth's poles, are caused by charged solar particles interacting with Earth's magnetic field and atmosphere. These displays become more frequent and intense during periods of heightened solar activity, which follow an approximately 11-year cycle. During solar maximum, increased sunspot activity and solar flares propel more particles towards Earth, fueling brighter and more frequent auroras. Conversely, during solar minimum, the auroral displays are quieter and less frequent. The sun's magnetic fluctuations ripple outward, and we witness them in the form of auroras painting the skies, serving as a reminder that space weather can transform the heavens with its subtle solar brushstrokes. Conversely, during solar minimum, the auroral displays are quieter and less frequent. The sun's magnetic fluctuations ripple outward, and we witness them in the form of auroras painting the skies, serving as a reminder that space weather can transform the heavens with its subtle solar brushstrokes. Comet tails, solar windsocks, always point away from the sun. As a comet approaches the sun, its icy surface begins to sublimate, releasing gas and dust that form a luminous tail. However, contrary to intuition, the tail doesn't trail behind the comet like smoke behind a train. Instead, it always points away from the sun, regardless of the comet's direction of motion. This phenomenon occurs because the solar wind and radiation pressure push the released material outward, creating two distinct tails, a curved dust tail and a straight bluish ion tail. The result is a luminous windswept signature tracing the invisible force of sunlight through the darkness of space. Some planetary moons, products of cataclysm, formed from giant impacts. The result is a luminous windswept signature tracing the invisible force of sunlight through the darkness of space. Some planetary moons, products of cataclysm, formed from giant impacts. Earth's moon is believed to have formed from a colossal impact between the early Earth and a Mars-sized object over 4 billion years ago. The collision ejected vast amounts of material into orbit, which gradually coalesced to form the Moon. Earth's moon is believed to have formed from a colossal impact between the early Earth and a Mars-sized object over 4 billion years ago. The collision ejected vast amounts of material into orbit, which gradually coalesced to form the Moon. Similar impact origins are suspected for other moons, such as Pluto's moon Charon. These violent beginnings stand in stark contrast to the captured moons of the outer planets, demonstrating that no single process can explain the formation of all satellites. Some moons launched it includes greetings in dozens of languages, music from around the world, and recordings of waves, birdsong, and laughter. Designed by a team led by Carl Sagan, the record is intended for any intelligent being who might someday encounter it. It is a message in a bottle cast into the vastness of the galaxy, a quiet greeting from our pale blue dot. Earth, a shared neighborhood, shares its orbit with co-orbital asteroids. Although Earth appears to orbit the Sun alone along its path, it shares its general region of space with small bodies known as co-orbital asteroids. These objects do not orbit Earth like moons, but instead follow stable, looping paths near Earth's orbit, shaped by gravitational interactions. Some, referred to as Trojans, congregate around stable Lagrange points located ahead of or behind Earth. Others follow horseshoe-shaped paths that keep them near but never colliding with our planet. These quiet companions are often temporary, captured and released over thousands of years. Invisible to the naked eye, they drift near us in space, fellow travelers on our yearly journey around the sun. Neptune, a late bloomer, was once confused with Uranus. Before Neptune was officially discovered in 1846, some early astronomers may have observed it without realizing its true nature. Due to its slow movement and faint appearance, it was occasionally meant for a fixed star or thought to be another sighting of Uranus. In fact, Galileo Galilei may have knowingly observed Neptune through his telescope in 1612 and recorded it as a star in his roots. It wasn't until mathematicians noticed irregularities in Uranus's orbit that Neptune's existence was predicted and subsequently confirmed. In a sky filled with countless wandering points of light, Neptune remained hidden in plain sight for centuries. The edge of the solar system, a boundary of influence, isn't defined by gravity alone. The sun's gravitational pull extends far beyond Pluto, holding onto distant comets and icy bodies in the Oort cloud. However, when scientists speak of the edge of the solar system, they often refer to the boundary of the heliosphere, the region where the solar wind meets the interstellar medium. This edge, called the heliopause, marks the point where the sun's magnetic field and particle flow cease to dominate. Gravity continues to exert its influence far beyond this boundary, but the energetic boundary of the heliopause is where the space between the stars truly begins. It's a subtle, shifting frontier, more of a change in pressure than in physical presence. Gravity continues to exert its influence far beyond this boundary, but the energetic boundary of the heliopause is where the space between the stars truly begins. It's a subtle, shifting frontier, more of a change in pressure than in physical presence. Planetary atmospheres, ever-changing, slowly leak into space. Even thick atmospheres like Earth's are not entirely permanent. Over time, lighter gases such as hydrogen and helium can overcome a planet's gravity and drift off into space. Planetary atmospheres, ever-changing, slowly leak into space. Even thick atmospheres like Earth's are not entirely permanent. Over time, lighter gases such as hydrogen and helium can overcome a planet's gravity and drift off into space. This process, known as atmospheric escape, is more pronounced on smaller planets with weaker gravity such as Mars and Mercury. On Venus, the absence of a global magnetic field has allowed the solar wind to gradually erode parts of its upper atmosphere. Earth loses thousands of tons of hydrogen each year through this process. Although it is readily replenished, the slow escape of gases represents a quiet leak into the void, a constant exchange between planets and the vacuum beyond. Some moons from rings may have formed from ring systems. Just as ring systems can decay and vanish over time or coalesce into planets, they can also give birth to new moons. In the case of Saturn, it's possible that some of its small outer moons originally coalesced from ring material that clumped together beyond the Roche limit, the distance from a planet within which tidal forces will disrupt a celestial body. Moons like Pan and Daphnis, which orbit within Saturn's rings, may still be accreting material from the rings today. These moonlets serve as quiet sculptors of the rings, their gravity carving gaps and creating waves in the icy bands that encircle the planet. Voyager 1, a silent ambassador, is still sending data from interstellar space. More than 45 years after its launch, Voyager 1 continues to transmit faint signals back to Earth, even as it journeys through the interstellar medium billions of kilometers from home. Its instruments continue to measure cosmic rays, magnetic fields, and plasma density in the space between the stars. Power is limited and systems are gradually being turned off to conserve energy, but the spacecraft continues to function thanks to a tiny nuclear power source and communicates via the Deep Space Network. Each signal takes more than 20 hours to reach Earth, a whisper from the very edge of human exploration. The solar system, a galactic traveler, completes a galactic orbit every 225 million years. While the planets orbit the sun itself is also moving, revolving around the sun, the center of the Milky Way galaxy. It takes roughly 225 to 250 million years for the sun to complete one orbit, a journey sometimes referred to as a cosmic year. During that time, the solar system drifts through different regions of interstellar space, potentially passing through galactic arms, star-forming regions, and clouds of gas and dust. This motion may influence comet activity, and on longer timescales, even Earth's climate. We are not fixed in space, but are part of a vast, slow spiral, riding the galaxy's arm like passengers on a cosmic carousel. And so our quiet journey through the solar system comes to a gentle close. From the inner world scorched by sunlight to the icy moons that whisper in the dark, we've wandered together through orbits, storms, and shadows, one sleepy fact at a time. If your eyes are already heavy, that's just fine. Let the last traces of starlight fade behind your thoughts and let your breath carry you softly into rest. There is still so much more to discover, but for now you've learned enough. You've traveled far, universe can wait until morning. Thank you for spending this time with me. And so, under the quiet stars, the story continues. I hope you sleep well and dream sleepily. Good night. Music. 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 Heat. Heat. Music. Heat. Heat. Music. 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 Heat. Heat. Music. 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 Thank you. Music. Music. Thank you. Music. Music. Thank you. Music. 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 Heat. Heat. Music. 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 Heat. Heat. Music. Music. Thank you. Music. 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 Heat. Heat. Music. 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 Heat. Music. Heat. Music. Music. Thank you. Music. Music. Heat. Heat. Music. 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 What are you doing? Music. 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 Heat. Heat. The soft melody began. A lullaby woven from stardust and dreams. It danced through the air, a comforting embrace after a long journey through the cosmos. The music swelled, filling the void with its gentle cadence. Heat. A sudden surge, a wave of energy washing over everything. The music pulsed with it, the notes shimmering and vibrating with newfound intensity. Heat. A second wave, even stronger than the first, brought a faint shimmer to the air, a visual distortion that hinted at something immense and powerful just beyond perception. Thank you, whisper. A gratitude breathed into the void. The music softened, taking on a reverent tone, acknowledging a presence, a guiding force. Thank you. Louder now, more confident, a recognition of the help received on this incredible voyage. Thank you. Whisper, a gratitude breathed into the void. The music softened, taking on a reverent tone, acknowledging a presence, a guiding force. Thank you. Louder now, more confident, a recognition of the help received on this incredible voyage. Thank you. Going through the starlit expanse, a heartfelt appreciation that transcended language. The heat intensified, radiating outwards, and the music shifted again, becoming a vibrant tapestry of sound and sensation. It painted a landscape of swirling nebulae and distant galaxies, a breathtaking vista of cosmic wonders. Heat. Hue. The whisper returned, softer now, fading into the background as the music grew more complex, more intricate. Grew more complex, more intricate. Was a song of creation, of boundless possibilities, of the eternal dance of energy and matter. Heat. The waves kept coming, each one resonating with the core of your being. It was a baptism of fire, a cleansing and a renewal. The heat was not destructive, but transformative. What are you doing? A voice breaking through the symphony of the universe. question posed to the very fabric of reality, a challenge to the forces at play. The music faltered for a moment, then surged back, stronger than before. A final overwhelming wave washed over you, and then the music faded, leaving behind only the soft hum of the universe, a gentle reminder of the journey that had just concluded.